All right, week 4. So today we're going to focus primarily on regression methods, and we will also end with how do we determine the size of our study. So again, just like in the previous weeks, a reiteration of where you can reach statistical support at the medical center. There's an entire department of faculty statisticians and staff who are able to help with protocol development, grant development, data analysis, manuscripts, things like that. We're in Robinson. You can go to the front desk there, or you can email me and I can forward you information about who to get in contact with specifically. These lectures are being recorded, and the link was sent to registered participants by email. These are going to be migrated over to YouTube once we clean up some of the audio from the first week, and then some of the issues from last week when we had to change classrooms in the middle of the session. This final day will be devoted primarily to regression analysis. What I hope to show you is that most of the common methods that we use are all really doing the same thing. They're just doing it in slightly different ways depending on what our research question is. Regression methods in general are used to describe relationships between different variables. For instance, when we have a single dependent variable, which we call y in most models, and one or more independent variables or predictors or covariates x, that is the most commonly applied approach for regression, regardless of what the combination of x and y actually is. There are methods, obviously, beyond the scope of this class that are not included here. Things like Poisson regression, negative binomial regression, time series, multivariate regression models where you actually have more than one dependent variable. You have more than one outcome, and you want to model it all together in a single simultaneous equation. So again, just to reiterate, this is kind of a simplistic look at what's available, but these are probably the ones that you all would be looking at to apply in your data. Anything beyond that, you would need to consult with a statistician. And I will also say you probably need to consult with a statistician if you're going to do Cox regression, because Cox regression has some key assumptions that we often fail to investigate before we report the results of that can very, very greatly impact the validity of those methods. So here I've just given you a nice little framework similar to some of the structures in the past, showing you which of the regression methods is appropriate or ideal given the combination of independent variable and dependent variable that you have. So for instance, linear regression, which is what we most of us think of when we hear the term regression, is a combination of continuous x's, continuous predictors, and a continuous outcome, y. So if you have, for instance, age with BMI, or age and oh my gosh, I'm trying to think of an example. I have an example later. Age and cholesterol levels, for instance. If you think you could describe the relationship between those two continuous variables using some kind of line, then that means linear regression would be appropriate. That does extend to more than one independent variable. The distinction between a single independent variable and multiple independent variables in a model is it's denoted by the term simple versus multiple. So if I say simple linear regression, you should understand that I have one x and one y. If I say multiple linear regression, I mean I have more than one x, but still a single y. And I'll show you examples of both of those shortly. A couple of other specific cases that technically are still linear regression, we'll also see that in a moment, involve differences in what our independent variables actually look like. So for instance, I already gave you an example where age was our predictor and it's continuous. What if instead of age we had something like sex or stage of disease or treatment received, exposure status? That would be a categorical independent variable, and the regression model that we use for that is ANOVA. We actually saw that last week, but I'm going to show it to you again and show you how it's doing the same thing as linear regression. A specific extension of that model is analysis of covariance, which we also call ANCOVA. And ANCOVA really is doing the same thing that ANOVA is doing. It's generally interested in comparing how patients respond under different conditions, under different levels of that categorical independent variable, but it also wants to additionally adjust for some continuous nuisance factor, like age. So when we have a little more complex model, depending on how it's structured, it could be analysis of covariance. If you have a categorical dependent variable, so now your Y, instead of it being BMI, maybe it is response to treatment, yes or no. In that case, what you're interested in doing is predicting whether or not, or the odds or likelihood of someone responding as a function of some X's. Regardless of what type of predictors or independent variables you have, you're probably going to want to start with logistic regression, because that logistic regression is a common tool that's used to estimate or predict the chances of some kind of event occurring. Extend that to incorporating the timing of the event as well as whether the event is occurring, and you get Cox regression, which is appropriate for time to event data. So let's take a look at linear regression first, because I think this is the best framework from which we can build on to just think about what regression is trying to do in the first place. So if we have two continuous variables, the relationship between those two variables might be one of functional dependence. So there's science behind the link between X and Y. When I say functional dependence, I mean the magnitude of the dependent variable is assumed to be determined by or dependent on the value of the independent variable. But the reverse is not true. So Y is Y in your model because it is dependent upon, functionally dependent upon X. If that's not the case, you might be more interested in looking at correlation. If there's no obvious independent variable and dependent variable, then correlation strategies might be more appropriate, where they don't try to assume the nature of the relationship, they're just trying to describe the strength of it. So some examples of this might be supplement dose and birth weight of babies. So if I increase, for instance, DHA to mothers, the dose that they're receiving from placebo up to some maximum acceptable dose level, we might also see changes in birth weight of infants born to these mothers. So that is an obvious functional dependence between birth weight, which is our Y, our dependent variable, and supplement dose, which is our X. Blood pressure and age is another example. We wouldn't think that age would change as a function of blood pressure, but we might think that blood pressure could change as a function of age. So if you have circumstances where there's not a clear X and Y, probably steer clear of regression methods because they're not appropriate for anything beyond functional relationships. Now, one of the caveats to this is that being dependent on something does not mean it is caused by. We can actually establish causality using regression, but causality is determined by the experimental design, not the statistical analysis method. So if we think back a couple of weeks when we talked about when can we assume cause and effect, there are some specific guidelines where many controls have to be in place to rule out nuisance variables, confounding variables, other potential sources of the relationship that we might see, aside from the X or the independent variable of interest. So again, dependent on, caused by, whatever you conclude from a regression analysis is dependent upon the circumstance that generated the data. If it's not a true experimental situation, then we don't want to try to stretch for that causality. Let's take a look at an illustration of simple linear regression. I have here what's called a scatter plot. This figure is one of the most common methods graphically to describe the relationship between two variables. So here I have pre and post test scores on 50 individuals, and I want to see how they're related. Does the pre-midterm exam score predict their post or final exam score? Are they associated? And also, how are they associated? So if I'm looking at the relationship here, I might want to describe this by a line, because it does look, if I look at this cloud of points, it looks like a line would be a natural tool to describe the relationship. If I saw some kind of curvilinear relationship, I probably would want to describe it with a curve, not with a line. So again, simple linear regression would not be appropriate. But if we recall our high school algebra, maybe even before that, the equation of a line, we can fully describe a line with two, I'm going to call them parameters because they're things that are unknown that we're going to try to estimate. We have the intercept, beta 0. The intercept is actually where the line crosses the y-axis at x equals 0. So it's a value, for instance, a value of the outcome when x is equal to 0. Beta 1 represents the slope. So this parameter describes how y changes as a function of x. So if I increase x, beta 1 tells me how I can expect y to change, either increase or decrease. Generally, beta 1 is the more important parameter here because that's the one that actually describes not only how y is expected to change as a function of x, but it also describes how strongly these two things are associated. If we again think back to the equation of a line, what's the slope of a line when y doesn't change at all as a function of x? What's the slope? It's horizontal. What's the value, though? What's the number that describes that 0, right? That says that y is not changing as a function of x. Another way to say that is that x provides me with no useful information about what y will be because they're not functionally dependent, at least based on the data. So if I get values of, if I estimate beta 1 to be very close to 0, that is evidence that there's no linear relationship, no strong or significant linear relationship between these two variables. Anything that's negative or positive will actually indicate some kind of linear relationship, either decreasing or increasing. Beta 0, the intercept, again, is sometimes not even meaningful because if the value of x equals 0 has no meaning, then beta 0, which represents what y is when x is equal to 0, really has no meaning. So we often, again, focus on the beta 1 parameter. The key to linear regression, just like it was with ANOVA and everything that we talked about before, is attributing variation or changes in an outcome to different sources. So in this model, there are two sources of variation. The first source of variation, we're going to call it the explained variation, actually comes from the functional dependence upon x. So as x changes, we can describe some of the variation or change in y using a line. However, if you look back at the figure, there is some deviation of the observed value of y. That's the vertical distance, right, of each of these points. There's some difference between those and that line, which is represented here. It's an example. It's not the exact one. Here in dotted blue. So they deviate, right? The observed values deviate away from that line, which is the tool that we use to estimate or predict y. That is what we call error. And it's, again, just the part of a person's response that is unexplained by the model. So just like in analysis of variance and other methods, the t-test, chi-square, we have some signal and we have noise. The signal is this explained linear relationship, that systematic component that looks like the equation of a line. The unexplained are the deviations of the observed values from that explanation, which we call epsilon sub I. And so what we want to do is pick values of beta 0 and beta 1 that minimize those epsilon sub i's, the errors, if you will. It minimizes, in other words, a good line will have values of beta 0 and beta 1 that minimize the amount of unexplained variation in the outcome. The best approach to this is what's called least squares estimation. We're not going to get into the mathematics. Just know that when we fit a linear regression model, the approach to estimation that gives us those best values of beta 0 and beta 1, just like with the t and the f and the chi-square, has some mathematical assumptions to it before it actually gives us values of beta 0 and beta 1 that are optimal. Optimal in the sense that it's maximizing the amount of explained variation in y and minimizing the amount of unexplained variation in y. We'll talk about what those assumptions are in a moment and how to check them. So if I were to perform least squares estimation on this data, why do I not see a hat there? Oh, because I didn't change it on both slides. I apologize. So this equation is actually wrong, because now what I'm trying to do is describe what I would expect y to be for different values of x after I've estimated the intercept and slope of the line. So I differentiate between the observed value of the post-test score from the estimated or predicted value of the post-test score by just putting a hat over y. And I didn't do that here, I apologize, so it could be a little bit confusing if you're interested in the notation. Just know that estimation yields the equation of that line, that optimal line, and it turns out it gives us an intercept of 0 and a slope of 0.545. The interpretation of those two estimates is actually pretty straightforward. So, for instance, let me explain the data a little bit more before I get into this. So these scores are pre- and post-test scores, and they're standardized. Does everyone know what standardized scores mean? So if I'm taking a test, I might get a 75% on it, which is my raw score, right? I got 75% of the material correct, 25% of it was wrong. But that might not reflect my actual relative aptitude for that material as compared to my peers. So I might be interested in seeing, or the instructor might be interested in seeing, how well did I do relative to the rest of the class? Am I above average? If I'm above average, how far above average am I? So one way to do that is to actually generate what's called a z-score. A z-score is just a standardized score where you subtract out the average and you divide by the standard deviation. So then my score now no longer reflects the percent of the material I got correct. It reflects how far above or below the average I am in units of standard deviations. So for instance, if my 75%, if the entire class scored, if the average of the class was 75%, and my exam score was equal to that average, what would my z-score be? 0, right? Because I center the score. So a 0 reflects the average value of the exam score. If I scored, if my z-score is 0.5, then I'm actually, since it's positive, I'm above average, and I am half a standard deviation above the average, where the standard deviation is the standard deviation of the scores in the class. If my z-score is 1, I'm 1 above. If it's -1, I'm 1 below. So we like z-scores when we're looking at relative performance as opposed to absolute performance. And test scores, very often that's the case, unless the score itself is like the ACT or the SAT, where it's kind of standardized by default. That makes sense whenever you get it. So this data is actually standardized. It's a standardized pre-test and a standardized post-test. And you can see the x-axis, the center is at 0, and it goes out to plus and minus 2 standard deviations. So this person right here scored really poorly on the pretest. They're 2.5 standard deviations below average. We don't know what their raw exam score was, but we know it's really bad relative to the rest of the class. They didn't score as badly on the post-test as this guy, but still didn't do great. Right now they're about 1.3 or 4 standard deviations below average on the post-test. So back to interpretation of the regression equation, now knowing what the data actually is, which is vital, right? We should have probably started with that in the first place. The 0.545 tells me how post-test scores are expected to change for changes in pretest scores. Or it also tells me what I can expect for 2 different subjects whose pretest scores differ by 1 unit or 10 units or whatever. So it's just allowing me to describe expected values of y as a function of x. One of the interpretations here is that a subject who scores 1 standard deviation above average, so 1 unit in x, on the pretest is predicted to score only 0.545 standard deviations above average on the post-test. So how did I get that value? I just plugged in a value of 1 for x. Another interpretation could be if I have 2 students, one who scored 0 and one who scored 1 on the pretest, how can I expect their post-test scores to differ? So the difference between 0 and 1, I can actually look at the value of y on the graph. So the person who scored 0 is expected to score about 0. The person who scored 1 is expected to score, oh, this is actually not the line because it's y equal x, is expected to score, if I plotted this line, about 0.545. So the slope not only allows us to calculate the expected value of y or predicted value of y for different values of x, it also allows us to describe differences in y for differing values of x. By the way, this example here where we have a slope that's less than 1 is an example of what's called regression to the mean, where individuals who score really poorly on the midterm exam are expected to score poorly on the final exam, but not quite as poorly as they did before. Likewise, people who scored really well before are expected to score really well on the post-test, but not quite as well as they did before. That's actually this concept of regressing toward the average in subsequent testing or in subsequent generations. That's actually where the term regression came from. When we interpret this intercept estimate, so B0, which is the value of y when x is equal to 0, it's also pretty straightforward. It's just plugging in x equals 0 to figure out what we would expect y to be. So in this case, it would tell us what we could expect a student who scored average on the pretest, how would they score on the post-test. And so since that intercept is 0, they're expected to score about 0. One of the other nice things that we might want to produce whenever we're producing these estimates, and they're easily attainable from any statistical software, we don't want to just provide estimates ever. We don't want to just say the mean is this or the standard deviation is that. We also want to provide a measure of the uncertainty or variability associated with our estimation. So confidence intervals should always accompany any estimates, including estimates like this where maybe we're estimating y. We also want to get a confidence interval on y, which provides us with kind of the range of likely values to expect for someone who scores a 0 on the pretest. The research questions that we address with linear regression have to do with, the association, the strength of association between x and y, but it's a specific kind of association. I alluded to the fact that if it's not linear, then we shouldn't be using linear regression, because though we can fit a line to any data, that line might not be the best means to describe the relationship. So always visualize the relationship first and make sure a line looks appropriate. If it looks curvilinear, you probably need to come talk to me, for instance, or talk to someone who's more familiar with fitting those kind of non-linear or curvilinear relationships to help describe associations. It also allows us to predict or estimate the outcome for different values of the independent variable. So for instance, what's the value of y? What value of the post-test score should we expect for a student who scored a -2 on the pretest? And again, what is the difference in post-test scores for individuals who differ on the pretest score by 1 standard deviation? When we do inferences in linear regression, we actually use a t statistic, and it's a really easy statistic. For example, this is just one example of a t. You take the estimate from the regression model, and you divide it by its standard error. And those in general will test whether or not the thing you're estimating is equal to 0 or not equal to 0. So here I'm showing you the test statistic for beta 0, not for beta 1. But if you look at any standardized output, it will look like this, where you get a coefficients table, and you'll have a row that corresponds to your intercept term. So this is the estimates and information about our estimation of beta 0, the intercept, and one for the slope, which is, again, generally the one we're more interested in. This is in scientific notation. The e to the minus point or minus 0.01 just tells me that I need to move the decimal place 1 to the left. This tells me I have to move it 16 to the left, so you can say that that's why I showed you that the intercept was essentially 0. So we get the values that tell us the line. The line is 0 plus 0.545 times x. We get standard errors associated with our estimates that, again, reflect the amount of variability or sampling variability associated with that estimation. So really big standard errors mean that we don't have a lot of precision in or confidence in our estimation. And then you see the individual tests from the t-test statistic. So these tests, the one in this first row, is actually the one that you see here. It's the value of B0 divided by its standard error, which gives us basically a t of 0. And then there's the p-value. And what that's testing, it's testing whether or not the intercept is equal to 0. And that's probably not a meaningful test here, right? We don't really care whether or not the intercept is equal to 0. We want to know whether or not post-test scores are changing as a function of pre-test scores. So the variable in the data set here was called midterm. And that t is large. It tells me that the observed estimate of the slope is actually almost 5 standard deviations larger than what I would expect it to be if there was no linear relationship between pre and post-test. So I really don't even need to rely on the p-value. I can tell from the t-value alone that there's a big difference, and it's a big difference in a positive direction. But the p-value tells me that this is statistically significant to several digits. What else do I want to say here? And so this t is actually testing these hypotheses. Why are the hypotheses about are x and y linearly associated, why are they framed in terms of the slope? It's because of what we just mentioned a few moments ago, where if we have a line where y doesn't change as a function of x, that line is horizontal and its slope is equal to 0. So the null hypothesis basically states mathematically that there's no linear relationship between x and y, that the slope of that line is equal to 0. And the alternative is that there is some linear relationship, either positive or negative, so beta 1 would be not 0 in that case. And again, the large t tells us that the value that we observed is actually very different from what we would expect it to be if the null hypothesis were true. It's very different than 0. Another test statistic that can actually be applied, and this is going to segue us back into analysis of variance and showing that ANOVA and linear regression are really doing the same thing. The F statistic can actually be used in this framework of simple linear regression, also in multiple linear regression. The F statistic here, if we remember back last time when we looked at the ANOVA table, remember the F value is a ratio of the two variances, where the variance in the numerator essentially describes the signal, the variance in the denominator essentially describes the noise. So this variance is the variance in the outcome that includes not only the error variation, but also variation that we want to attribute to the independent variable here, which is midterm. So we can see that it's large relative to the error variance. In fact, the F value tells me that the variation in the numerator is 22.5 times that of the denominator. So it's a much bigger variance, which tells me there's a huge signal here for some treatment effect, if you will, where the treatment is the information from the pretest score. So ANOVA and regression, again, are doing the same thing. Notice the F value, 22.4, corresponds to a p-value of 1.675. If I go back to my previous table where I showed you the t-value, the value for the t-test, the p-value for that test is the same p-value. It's because they're doing the exact same test. They're both testing these hypotheses. One is doing it in a slightly different way than the other, but they're mathematically equivalent. The only difference, the only time you would really prefer the t-test over the f-test is if you have a directional hypothesis. F is non-directional. F can't tell us whether the midterm is positively related to the final or negatively related. It just tells us that there is an obvious association. However, the t, by definition, tells us whether it's positive or negative, because if this estimate is positive, the t will be positive. If this estimate is negative, the t will be negative, because it will tell me, again, how many standard deviations below what I expect the actual estimate is. So the t is what's called a directional test, and it should be employed whenever you have an alternative hypothesis that, wants to be able to demonstrate that there is a positive linear association or a negative linear association. In other words, that beta 1 is either greater than 0 or less than 0, because the F won't allow you to test that. It only allows you to test whether it's equal to or not equal to 0, because it's a non-directional test. So again, segueing back into ANOVA, ANOVA is just regression. It's a special case of linear regression where our independent variable is categorical. So generally, in biostatistics, the independent variable, the categorical independent variable, is describing subjects' treatment assignment or exposure status. Analysis of covariance, which you might be a little bit less familiar with, is a special case of linear regression. It's a special case of ANOVA. It's basically just ANOVA, where we're trying to look at the relationship between an outcome and some treatment, categorical treatment factor, while controlling for or adjusting for a continuous nuisance factor. So I have multiple variables. One is categorical, and it's the primary predictor or independent variable of interest. And then I have a nuisance variable, which is continuous, that I have to adjust for. Let's take a look at a motivating example of ANOVA, and I'm going to show you how ANOVA is actually just a regression model. Suppose we have two different training programs that are both designed to improve employee satisfaction, and we want to compare their effectiveness. We have some kind of employee satisfaction scale that's gives us a value between 0 and 100, where low values are equivalent to low satisfaction. the data that we get from this study could support, again, one of our two competing theories. The first theory is that employee satisfaction is associated with the type of training program they're receiving. Notice employee satisfaction is continuous. It's a satisfaction score that's continuous. It's our outcome, our dependent variable, and X, our categorical independent variable, is displayed across the bottom. It's program 1 or program 2. So before we had a scatter plot, and we could visualize whether a line made sense. Now we don't really, I mean, we could do a scatter plot. I'll show you a scatter plot of this data in a moment. It really doesn't make sense to look at it that way. But we prefer box plots in this case because people are naturally grouped according to the independent variable. And so here we would see differences, right? Differences in satisfaction scores between the two programs. Here we see no differences, really. So theory 1 is that they're associated. Theory 2 is that they're not associated. So this is the alternative hypothesis, and this is the null hypothesis, just like we saw with the linear regression. When we do simple linear regression, again, we have an example here, the midterm or pre-test and post-test. We generally look at a scatter plot, visualize that a line is appropriate, and we're able to estimate that line, which gives us the ability to describe changes in a continuous outcome as a function of a continuous independent variable. And the questions, the research questions we answer in this framework tend to be about association. Are the two associated? What does that association look like? For instance, what would I expect the outcome to be for a 1-unit difference in X? And these questions are answered using a line because the slope conveniently describes what we're after. However, the question in ANOVA is the same, but it makes sense to answer it in a different way. So we're still interested in whether or not X is associated with Y, but we really aren't asking what the slope is here. What we're asking really is how does the average response differ between these two programs? It turns out that's the same as asking what the change in the outcome will be for a 1-unit difference in X. So mathematically they're the same. We can still answer it with the slope because it turns out that the average, the expected outcome under program 1 and the expected outcome under program 2, we can actually write them as a function of the intercept and slope from the linear regression model. So, for instance, the average employee satisfaction score under, let's say, the standard of care or the reference program is actually just the intercept term from a regression model, and the expected employee satisfaction score from the experimental training program, which we'll call program 2, is the sum of beta 0 and beta 1. So that gives us mu 2. So getting beta 0, I could fit a linear regression model to this data. You see the scatter plot now, right? You see the scatter plot of the individual observations. A line does look like it will do a good job, but it's misleading in the sense that X is only ever equal to 0 or 1 to indicate program 1 or program 2. The other reason why we don't tend to use just linear regression when we have a question like this is because why would I ever want to produce output that includes a beta 0 estimate and a beta 1 estimate and then have to calculate mu 1 and mu 2, which are the parameters I'm really after? So why not use a method that just gives me the things that I want? The average value of the employee satisfaction score when program is equal to 1 or program 1 versus program 2. And that's what analysis of variance does. So notice the model here at the bottom looks different than it did before. This is what's called a cell means model. It goes really well with a one-way ANOVA where we just have a single X that describes some kind of categorical factor. So mu sub I represents the expected or predicted outcome for each of the I equal 1, I equal 2 programs here. So mu 1 is what the line predicts Y to be for program 1. And mu 2 is what the line predicts Y to be for program 2. And when I apply ANOVA as opposed to linear regression, I don't get beta 0s and beta 1s. I get mu 1s and mu 2s, which are the things that I want anyway. So the questions that we ask, it's a little bit different from regression, but it's really the same. We want to know, how does the average outcome differ across the different levels of that categorical factor X? And the ANOVA model describes that very well. This is the cell means model. We also have something called the effects model, which, again, depending on how we apply it, can actually address the same question in a slightly different way. So if I want to describe the average response under different programs, I probably want to have some kind of formulation that will provide me with the mu sub i's. But if I'm interested in how maybe different programs differ from some condition, I might want to include what's called an effects model. I'm just going to quickly go through this to show you what those new Greek letter taus represent. So the taus describe how employee satisfaction differs within the two groups from the overall average level of satisfaction. So the overall average level of satisfaction is here. That's what this mu parameter represents. And the tau sub I describes, again, is it above average or below average? So it looks like here in program 2 has above average levels of satisfaction, and tau 1 will be negative because it's a deviation below mu, will result in employee satisfaction below average. Let me stop there. Any questions about how ANOVA and regression correspond? You can interchange them. You can do ANOVA to regression, you can do regression to ANOVA. You just might make your work harder when it comes to describing the relationship. Here's a different research question. Suppose we want to compare the effects of several training methods on the performance of cross-country athletes. So our Y here is continuous. It's their performance at the end of their training, measured by time to complete a 5K. And the treatment here, the independent variable, represents some categorical factor that describes which training method they used. The problem with just doing ANOVA on this, where I have Y as a function of categorical X and then just compare the outcome across the different training periods, is a problem that's very common in clinical research, where the baseline value is actually predictive of the final value. So in pre and post-test situations, in weight loss, people who do really well at the beginning might also do really well at the end. People who do poorly at the beginning might also do poorly at the end. It might also, their performance at the beginning might also be predictive of changes in performance. So you could get individuals who have a lot of room to grow, who grow more than individuals who are already really good at baseline. That's what's called a ceiling effect. So when you have a nuisance factor, like in this case, athletes' performance prior to actually doing this study is probably predictive of their performance at the end of the study in some way. That's a nuisance factor. We want to be able to account for that when we compare the different training methods. We can account for that in several ways. So if we think back to experimental design, we want to in some way control for this additional variability in our outcome, or adjust for this additional variability in our outcome so we don't miss the signal in the noise. There are possibilities that include designing your study to control for that using something called a block design. So if you're able to measure performance prior to starting the study, then you might divide athletes into different groups based on which athletes have very similar baseline performance. And that allows you to then randomize within the block the different training methods, and then you have an apples to apples comparison, because I don't have all of my really good athletes all in one training method, or all of my really poor athletes in a different training method, which could confound the comparison. So blocking adjusts for this, or accounts for this variability in the design itself. Another way that we often approach this is by instead of just looking at their response, their 5K time at the end, we might look at their changing response. So measure their baseline performance, then their performance at the end, and calculate some kind of change score. The problem with that is that you actually lose some information, because better athletes might experience more improvement or vice versa. And that's the problem when I mentioned like a ceiling effect or a floor effect. Incorporating a change will not allow you to account for the fact that change itself might be related to those baseline values. The third and probably preferred approach is to include their baseline 5K time as a covariate in the model, and that is where we get analysis of covariance. So ANOVA is applied whenever you have a nuisance factor or an addition, any factor that can help explain why your outcome, that can be included in the model. In this case, if we can measure it on all of our subjects, we should incorporate it, and that will help reduce the amount of unexplained variability in Y and give us a more powerful test of the different factors that we're comparing. One of the caveats to at least the simplest ANOVA model has to do with how that nuisance variable, what it looks like in each of the quote-unquote treatment groups. So the framework here, I've shown you here on the right. What I've got here along the x-axis is the nuisance variable. In this case, it's baseline performance. On the y-axis is the outcome, which is their performance after the training period. And then I've got two lines that describe the relationship between that nuisance variable and the outcome in the two different groups we're comparing. What do you notice about those two lines? They're parallel. That's important because the fact that the relationship between the nuisance variable and the outcome is the same in the groups means we have a very simple model that we can apply. If you, however, see that, for instance, has everyone here heard of the term interaction? Interaction would result in lines here that are not parallel. It would tell me that the impact of this nuisance variable is actually different depending on which treatment was received. I might see a stronger linear association in one group and a less linear association, or maybe no linear association in another group. So we have to visualize our data, and I'll show you an example of that before we get to the end of the material. But just know that this is generally how we approach analysis of covariance. We need to visualize and make sure that the relationship between the nuisance variable and the outcome is the same in all of the groups being compared. We also have to assume that it's a linear relationship. Just like in linear regression, we had to assume a line was appropriate. A line needs to be appropriate before we apply the model that we have here. If that's the case, if the lines are parallel and the lines are appropriate, then this is the simplest model that we can use. Notice it looks like a combination of the ANOVA model right here. Remember the overall average response plus some effect on the response as a function of which treatment they received. These two together describe athletes, the average response, if you will, for athletes receiving the ith treatment. But look at this right here. This looks like the slope of a linear regression model, and that's what it is. Only the slope here describes how x is changing as a function of y, just to get rid of that unexplained variation to account for the nuisance variable so we can get a powerful look at what the actual impact of training program is. A couple of things to note also. I wanted to show you, so the power of a test reflects its ability to detect a meaningful difference. So if I have a really powerful test, if there is a difference there, I will be able to find it with a significant p-value. So higher power is obviously better. Notice the relationship here between the slope and power in analysis of covariance. If my slope is equal to 0, meaning there's no linear relationship, the nuisance variable actually isn't a nuisance variable at all because it has no impact or predictive power for the outcome, then if I do analysis of covariance, I really get no benefit because that nuisance parameter doesn't describe any additional variability in the outcome. So I could just do ANOVA and get the same level of power in my test. So again, just to reflect what the y-axis is representing here, it's the difference or the gain in power if we were to apply analysis of covariance over analysis of variance. So a slope equal to 0 tells me that there's no linear relationship. There would be no gain, no benefit from doing that more complicated model. However, if I get a really large slope coefficient, that tells me that my nuisance variable is really highly associated with my outcome, and it's probably doing a good job of explaining some of that additional unexplained variability. Notice the gain in power here. So the power is actually, 90% higher, right? So we want to apply analysis of covariance instead of ANOVA when we have evidence that some factor is linearly associated with the outcome, and we can account for it in this model. The evidence visually of the treatment effect has to do with the separation of these lines. So the bigger the separation, the bigger the difference in responses in the two groups. So let's take a look at an example revolving around childhood abuse. The research question has to do with whether or not individuals with a history of childhood sexual abuse demonstrate higher levels of PTSD than those with no history. So if I have a group of individuals and I ask them give them a questionnaire to measure their PTSD as adults, and also ask them about their history of childhood sexual abuse, I can classify them according to that independent variable, which is again categorical, and then visualize their differences in PTSD levels between the two groups. So this is a classic ANOVA situation, categorical X, continuous Y. The problem is there's a nuisance factor here that we probably want to also measure and account for, and that's a history of other abuse. So what other things could cause variation in PTSD levels in individuals? A lot of things, but an easy one to measure is other abuse. For instance, were they physically abused as opposed to just sexually abused? Because what you might get is someone who was not sexually abused, but who was physically abused, who shows really high PTSD levels. And so not knowing their physical abuse history could actually lead us to an incorrect conclusion about the relationship between sexual abuse and PTSD levels in adulthood. So what I've done here is, again, how do we visualize this relationship between a continuous nuisance factor, a categorical treatment factor or factor of interest, and outcomes like PTSD. Along the x-axis, I have physical abuse. This is measured by a standardized questionnaire. On the y-axis, I have the PTSD score, and I've labeled the individual by whether or not they have a history of sexual abuse versus not. And I see an obvious clustering here. Does everyone see the clustering? I see that those that are abused are in general higher on the PTSD scale than those that are not abused, the dark ends. But I also see separation here in those that have physical abuse and their likelihood to actually also suffer from childhood sexual abuse as well. So it's important to control for this nuisance factor in any comparison of these two groups as visualized here on screen. So this is just an analysis of covariance. I'm really interested in the average PTSD levels in the two groups, the red and the black here, the abused and non-abused. But I need to account for the increasing PTSD levels that we see as a function of increasing physical abuse, the nuisance factor. And so fitting this model gives me the results, just like we saw before, estimates of the intercept, which has to do with some level of baseline PTSD values, the slope parameter, which describes how PTSD levels are changing as a function of childhood physical abuse. So for any two individuals whose childhood physical abuse score differs by, let's say, 1 point, their PTSD levels are expected to differ by 0.55 points on that scale. And then this 6.2728 actually describes the difference in PTSD levels between the control group, the non-abused, and the abused. And notice that this 6.27 difference, which describes, again, the separation between these two lines, it's the same regardless of what level of physical abuse those individuals might have encountered. So having the ability to have equal slopes simplifies how I would describe the impact of sexual abuse, because it turns out, if this model is appropriate, I can talk about that without even having to frame it in terms of the level of physical abuse that these individuals are suffering, because regardless of the level, if I have two individuals who have similar pasts with physical abuse, I can describe their differences in PTSD for sexual abuse versus non-sexual abuse using the 6.2728. So it's the expected difference in PTSD for individuals who are abused versus non-abused. They're 6.3 points higher. You can see the t-values just like we had before in regression. They just basically test whether or not these factors are zero or non-zero. And so this tells me that there is some effect of sexual abuse. Any questions about analysis of covariance? Since this is technically a multivariable model, so remember at the very beginning we talked about simple linear regression versus multiple linear regression. Even though it looks like I have a single x in this model, I actually have two x's, right? I have the continuous x, which represents the childhood physical abuse score, but I also have a categorical x that differentiates individuals into two different groups according to their past history of childhood sexual abuse. And so the x isn't here, but it actually is. It's just a categorical, it's like a dummy factor, a dummy variable, if you will, where it flags individuals with the condition and doesn't flag those without it. So this is what's called a multivariable or multivariable or a multiple linear regression model. When we have multiple independent variables, we have to be careful how we interpret the individual estimates. I mentioned here the interpretation of 6.27, and that is that individuals who have a history of childhood sexual abuse can be expected to have PTSD levels of 6.3 points higher on average than individuals without a history of childhood physical abuse. And it turns out because of the model that we have here, that is true regardless of what level of childhood physical abuse they had. In general, though, we have to be careful about how we frame our interpretation when we have multiple variables in a model for Y. Suppose we have a linear regression model. In this case, it's multivariate linear regression model. Multivariable, sorry. And our outcome is birth weight, and we have a couple of predictors. The predictor of interest is dose. I'm giving a dose of a supplement to mothers, and I have a placebo and let's say a couple of increasing doses. But I also want to account for gestational age of the baby and their gender, because these two nuisance variables impact the outcome, birth weight, and accounting for them in this analysis will actually give me a more powerful look at the impact of dose on birth weight for these babies. So let's suppose I fit a model and I get an estimate of the beta 1, which describes how birth weight changes as a function of dose. How do I actually interpret that? I can no longer just say birth weight changes by this much as for every 1 unit change in dose. I have to be careful to frame it in terms of the other nuisance variables, because this only applies among babies who have similar gestational age and are of the same sex. So whenever I talk about the slope for the treatment factor here, I have to frame it in terms of among babies of the same sex, among babies of the same gestational age. This is how birth weight is expected to change as dose changes. This is particularly important when it's possible that the relationship between the treatment factor and the outcome could vary, for instance, between male and female babies. Maybe female babies benefit more in terms of their birth weight from this supplement for whatever reason. So then this beta 1 would be different for female babies than it would be for male babies. And so I would have to frame it that way. It could also be different depending on gestational age. If we have preterm babies, we might see a benefit, whereas for full-term babies we don't. So the beta 1 coefficient could actually be a function of the gestational age, which would be a much more complicated model than just a model that has X1, X2, and X3 in it. So we have to be aware of the possibility of this concept where the effect of one of the predictors is actually a function of one of the others, and that's what's called interaction. So if you think about that prior to actually analyzing your data, you should know, based on, again, kind of the functional dependence of these variables, whether or not interaction is possible. If it's a possibility, you should always test for it, and you can do that very easily. But again, because of the time that we have available in the class, I don't have any examples of interaction. I could show you what interaction would look like in analysis of covariance very easily. It's really nice to visualize. What would interaction between childhood physical abuse and childhood sexual abuse, my two predictors in this model, what would that look like for my regression lines here? How would it change the lines? They could potentially touch, right? The slopes would be different. They might cross completely. They might slightly come together on one end or the other. In other words, interaction is generally, in an analysis of covariance, what's called an unequal slopes model, where you actually allow the slope estimate to be different between these two, which again becomes a more complicated model, but it would be something that you could visualize by just looking at your data. If you get into things that are that complicated, I would encourage you to consult with a statistician before you run your analysis. Yes? This is linear regression. You just include their sex in the model. It's a categorical factor, and you just include it. So you would have a flag in your data set that says, if let's say all male babies you flag with a 1 and all female babies you flag with a 0, and then include that variable as part of your model. And what it will do is account for differences. You'd have to be very careful again, though, because if you think that dosing mothers with male babies could impact birth weight differently than dosing mothers with female babies, then it's not as simple as just including their sex in the model. You have to actually include what's called an interaction term between sex and dose, which just multiplies. It just multiplies dose by their value of the sex variable, the flag for sex variable. But again, it becomes kind of more complex than just this, and you would need to, if you were to take a full class in regression, you would see interaction, and you would be adequately trained to do it. So multivariable regression, again, sometimes called multiple linear regression, is just referring to the fact that we have more than one predictor. Simple linear regression means linear regression with a single predictor. A one-way ANOVA, that's a specific term for indicating that ANOVA has a single X. You have one factor. It's called a one-way ANOVA, and that's an example of simple linear regression. Analysis of covariance, however, is multiple linear regression because you have the categorical X and you have the continuous X for the nuisance factor. And that falls under the multiple linear regression umbrella. And we already talked about how we interpret results in multiple linear regression. We have to be careful about interactions. We have to frame any discussion about any one particular relationship in the context of what values the other predictors actually have for that comparison. Now, how do we check assumptions for linear regression, for analysis of covariance, for analysis of variance? There are primarily 4 assumptions that you need to look at, and for the most part, if you have a large enough study, you can do this all visually. You can do a scatter plot. Let's say we have simple linear regression. We do a scatter plot. We can see whether or not X and Y, whether or not a line would adequately describe the relationship, or if it should be some kind of curvilinear function. So if a line is appropriate, then they're linearly related. That's the first assumption. The second assumption is whether or not the variation in the outcome is constant across all values of X. So an example of that in analysis of variance, ANOVA, which is simple linear regression, we saw last week, where we saw one group had a box plot that was very short, another group had a box plot that was very spread out. That's unequal variances. And then the same has to apply when we have regression. So you'll recall from the scatter plot, let's go back to the very beginning. The scatter plot of this data showed me that I have approximately equal variation in Y. So I'm looking at how the dots are vertically scattered across all value of X. I don't see any systematic pattern. For instance, the spread of the Y values is about the same across all X. It would be problematic if I don't know why it's not letting me draw. It would be problematic, for instance, if I had points really tightly scattered here that got increasing as X got larger. You'd see kind of a megaphone shape either in one direction or the other. That can greatly impact the validity of your estimates and your ability to actually detect a relationship between X and Y. So visualizing, again, just a scatter plot will tell you whether or not variation in Y is constant across all values of X. Does it appear to be increasing as X increases or decreasing as X increases? If that's the case, then you have a problem with one of your assumptions. Are the errors normally distributed? So when we talk about normally distributed errors, this requires one quick check. You can look at a QQ plot. QQ plot is just a way to assess normality. You can save the error terms from your model, which is, again, in all statistical software packages, relatively straightforward, and just plot a histogram of them to see if you have a nice bell-shaped curve. Are the data from a random sample? So again, knowing the experimental scenario that generated the data is important, because if you're taking repeated measures over time on individuals and throwing them all into a big pot and then analyzing it using a regression line, you have dependence in some of those observations, which probably needs to be modeled. So the idea that you have a set of independent observations, that each one reflects an independent subject, and that there's no spatial correlation or temporal correlation in the data that might need to be accounted for. That can also impact your results. Generally, to assess the assumption of independence, which is what this fourth bullet says. You have to know how the data were generated. Where did they come from? What are they on? Are they on the same people? Are they on different people? Are they somehow naturally paired or matched or not? So understanding the source of the data, how the data was collected, really allows you to assess that assumption. There's really not a visualization of it unless you have some measure of the timing of the data included in your data set, or like a geographic location of the data point in your data set that would allow you to visualize it by time or space. And then for analysis of covariance only, that simplest model, again, assumed that the slopes, that the relationship between the nuisance variable and the outcome was the same in all groups being compared. And that assumption is equal slopes. You can actually test that in the model, or you can visualize it. And what you're looking for are similar slopes. So when you plot your data, does the relationship between X and Y look the same in all of the groups that you're comparing? Okay, now we've gone through, in that table, the first row. We went through linear regression, we went back over ANOVA, and we introduced analysis of covariance to show how they're all related and how they're different. Logistic regression is a very different animal, even though, again, it's still a regression model, and the right-hand side of this mathematical equation looks a lot like a simple linear regression model. But what's on the left-hand side here now? This is something called the log odds, which is what makes logistic regression a little bit more difficult to visualize and interpret. Logistic regression is applied when you have a categorical outcome. Generally, the outcome could be a success or failure, yes, no, responded, didn't respond. So you have a dichotomous outcome and any kind of predictor, any kind of independent variable X. The model looks like this. Again, X, this right-hand side is still the equation of a line, but instead of X predicting Y, X is predicting essentially some function of the likelihood of this event occurring. So if Y is death, for instance, death either occurs or it doesn't, so it's a dichotomous outcome. I might be interested in predicting the risk or the odds or the likelihood of death occurring as a function of some predictor, X. And that's what this model will do. It does it through the log odds. This is the odds. Pi here, notice, is just the probability that the event happens. So if Y equal 1 is a flag that an individual responds to treatment, then the probability that a patient responds to treatment is represented by pi. So the inside of this is the probability of a response divided by the probability of not responding, right? They either respond or they don't. And then taking the log of that. So again, it's not a straightforward relationship, but it does provide some meaningful information about how the chances of responding differ or change as a function of X. What we often see here visually are plots like what we see on the right. Notice we have a scatter plot. Along the x-axis is our predictor. In this case, it's temperature. Along the y-axis is our response. Remember, our response is dichotomous. They either did respond or they didn't respond. But we see a relationship here, right? Let's ignore for a moment that curve. Low temperatures tend to result in no response. The zeros are all kind of on the low scale. The responses all tend to be at higher temperatures, but there is kind of a range of temperatures that could result in either a response or a non-response. And so what we're trying to do here is classify. What we're trying to determine who is likely to respond as a function of their independent variable or predictor here. The usefulness of any model is measured by how well it classifies individuals into responders or non-responders based upon their predictors. So let's take a look at a relationship where the outcome is death. A logistic regression model that can be used to describe the relationship between some treatment, where treatment is either some standard of care or some experimental intervention. It's categorical, and the outcome is their status, let's say, at the end of a year They're either dead or alive. Again, pi represents the probability of the event occurring in the time frame, and we're modeling it using a logistic regression model. We have some kind of flag for our categorical variable, either 1 or 2 or 1 or 0, and then we run this model. Let's suppose we run the model and we get an estimate of the slope here, beta 1, which describes how the left-hand side of this equation changes as a function of x changing. So if we get a slope of minus 0.69 tells me that this thing is expected to decrease by 0.69 units for every 1 unit shift in x. But how do we say that the log odds of death decreasing by 0.69 units, does that make any sense? It's not interpretable really directly. So we have to apply a little bit of mathematical twisting, if you will, to the results to get an interpretable conclusion. And that turns out, again, it's generated by all statistical software if you know how to ask for it, but sometimes you don't know how to ask for it. So if you see estimates of the slope, just exponentiate it. So e to the estimate of beta 1 actually gives us something that's interpretable. It's the odds ratio that relates treatment to the risk or the probability or chances of death. So if I exponentiate negative 0.69, I plug it into my calculator, it gives me 0.5. Remember odds ratios from, did we talk about them last week or the week before? A ratio of 1 indicates that the odds or chances are the same for the numerator group as they are in the denominator. In this case, the numerator group is the treatment, the experimental therapy. The denominator is the control. A value of a ratio less than 1 indicates a decrease in odds. A value of a ratio greater than 1 indicates increasing odds associated with treatment. So it makes sense that if I have a negative slope, that I would see somehow decreasing chances of death occurring with treatment relative to the standard of care. But to quantify that, I have to exponentiate it, and it gives me 0.5. So 0.5 is 0.5 units below that value where the odds would be the same, which is 1. And so the interpretation is that we see odds of dying decreasing by 50% in treatment relative to standard of care. 1 minus 0.5 gives me 0.5. That's a 50% reduction. Reduction because it's below 1. What if we fit the model and we saw an estimate of the slope of 0.41? Again, the slope itself is positive, which tells me as x is increasing, whatever's on the left-hand side of that equation is also increasing, which, again, the left hand describes some measure of the likelihood of death occurring with treatment. So we know that there's an increasing relationship. In other words, treatment is associated with some kind of increase in the odds of death. In this case, exponentiate that, we get 1.5. Now we're 50% above 1, which means we see an increase, a 50% increase in the odds of dying in the treatment compared to the standard of care. It's important anytime you do a model like this that you understand what's in the numerator and the denominator of your comparison. So make sure that you know that the treatment is actually in the numerator versus the denominator. And the statistical software that you use should tell you in its help which one it's by default putting in the numerator and the denominator. Sometimes it does it alphabetically. So if you have a name for each of your treatments, it'll take the one that's first in the alphabet and put it in the numerator, or excuse me, in the denominator, which might not be what you want it to do. So you might have to tell it, no, this is the control group, put that in the denominator. So always be careful in understanding what the method is doing, what your tool is doing before you interpret. Again, the positive slope reflects the fact that we have increasing chances of death. So that was an example of logistic regression when X was reflecting some kind of treatment, standard of care versus control. So similar to ANOVA, comparing an average outcome across different levels of a categorical factor. Logistic regression can compare the odds of an event occurring across different levels of a categorical factor. It can also apply when X is continuous. So what if instead of X being the treatment they received, what if X is just age? It's continuous. Y is still, though, representing whether or not death has occurred during a particular study period. So we have the same model. X is different. It's continuous now. And we fit the model and we get estimates of the slope, describing the relationship between age and the left-hand side of that equation. If we exponentiate the value of 0.095, which is what we got for the slope, that tells me how the odds of death are changing for every 1 unit change or 1 unit increase in the X in this case, just like before in regression. So for every 1 year increase in age, the odds of dying increase by 10%. The 0.1, again, 1.1 minus 1 gives you the 0.1, that's 10%. That's where the 10% comes from. The positive sign for the slope indicates the fact that it's an increasing relationship. If we had a decreasing value, it would be for every 1 year increase in age, we would see some kind of percentage decrease in the odds of death. I think that's this is a typo. I'm seeing a decrease here. That should say increase in the chances of death. Now let's take a look at Cox regression, which is the last type of regression model I'm going to touch on. I'm not going to do a lot with this because I would not encourage you to, on your own, ever perform a Cox regression because, again, you can see how logistic regression is a little bit more. I didn't even talk about checking assumptions for logistic regression just because you don't have the nice histogram kind of stuff that it's easy to access. Cox regression is even more complex in that it's incorporating not only whether or not the event is occurring, like logistic regression, but it's also incorporating the timing of the outcome in the model, and it allows you to adjust for, again, other potential predictors or nuisance variables. The distinction between logistic regression and Cox regression is kind of what you get from the results in terms of interpretation. So it's the distinction between what we call a rate and a proportion. When I say the word rate, I think that most of us understand that that comes with some time component to it, right? When I say rate, it's like this per second, this per month, this per year. Proportion does not convey that same meaning. And that's really the difference. So when we talk about the hazard rate or the incidence rate, we're talking about how the event is occurring per some unit of time. When we talk about a proportion, we're just talking about what fraction have it or don't. So the two things that we generally can talk about with Cox versus logistic regression, the incidence rate, which is the hazard rate, which we referred to a little bit last time, is again how events are happening per some unit of time, and the cumulative incidence, which is a proportion, which is generally what we're analyzing when we do logistic regression, is the proportion of events that have occurred, let's say, in the entire study period. So when we have a hazard ratio, it's very similar to an odds ratio. The hazard ratio is a ratio of incidence rates, in essence. It's kind of a simplification of it. The odds ratio is a ratio of proportions. Logistic regression aims to estimate the odds ratio. Cox regression estimates the hazard ratio. And again, because Cox regression takes into account whether or not the event is occurring, but also its timing, you actually get a more powerful look at the impact of an exposure or a treatment on a population if you're able to do that. One of the key assumptions of Cox regression has to do with proportional hazards. Has everyone heard Cox proportional hazards regression? Okay, that's probably why it's misapplied very often. Proportional hazards, being in the title, tells us something about when the method can be applied. It can only be applied when the hazard function in the groups being compared are proportional, which basically means that they're similar, they're parallel. So for instance, it's always easy to assess it visually, and we can do a visual assessment of whether or not the hazards are proportional in two groups being compared by just looking at the Kaplan-Meier survival curves. So what I have here on the left is an example of what's called proportional hazards. The two groups being compared, again, along the x-axis is time, along the y-axis is the probability of the event occurring by that particular time point. At baseline, we're at 100% because everyone's alive. But then we start to see drops in these lines that are associated with the event occurring. Let's say the event is death. When we see rapid drops, the risk of death at that particular time point is higher, right? Because the curve is dropping more, reflecting more deaths occurring. If it levels out, the risk of death is actually decreased because we see fewer events occurring in that unit of time. But notice that we see a difference that starts early, and it's relatively similar across the entire curve. So that's when we have proportionality of hazards. The differences in risk are found early and maintained throughout the entire studied period. It's possible, though, that you get changing differences. So we have what's called converging. That's where you do see a difference in the risk early. It actually gets big and bigger and bigger, but then it comes together at the end. They converge. So you'll know right away if you have lines that cross, survival curves that cross, that you don't have proportional hazards right away. Converging versus proportional versus diverging. You might say, well, what's the difference between proportional and diverging? Well, I think it's pretty clear in this circumstance that there's no effect early, and that the effect shows up and is maintained late. Here, it's still maintained at the end. So these two scenarios, if you're comparing two groups using Cox proportional hazards regression, these two scenarios will provide you with an invalid result. You won't know your type 1 error, your chances of it being a type 1 error. You won't know your chances of it being a type 2 error because you're applying an inappropriate method. There are methods that are appropriate when you have converging or diverging methods. The log rank test is actually always appropriate. It's more powerful in certain situations, but it's always appropriate because it doesn't require proportional hazards. The problem with the log rank test is that it doesn't allow you to adjust for nuisance, other factors that could impact an individual's survival. But proportional hazards, this is the only scenario where Cox regression is actually appropriate. Cox regression is not really a parametric method like the t-test or linear regression, where we have full-on assumptions that we have to verify. It's semi-parametric. It's a mixture of parametric and non-parametric. Not really. It's not fully parametric, if you will. But there are assumptions that you have to check. The Kaplan-Meier method that generates the survival curves is actually, it's non-parametric. We don't have any assumptions. But there are also parametric methods that can allow you to estimate the survival times. So if you've ever heard of an exponential model, that is actually assuming some parametric function of the survival function in order to estimate it. So some assumptions have to be met. The nice thing about Cox regression, again, it can accommodate multiple predictors in a single regression model. And it's also easy in Cox regression to incorporate, again, those time-dependent covariates that are changing in value over the course of the observation period. The example that I gave last time was oral contraceptive use in athletes. They might switch on and off. And so if we don't know how that exposure is changing over time, we might make the wrong conclusion about the associated risk with fractures. So again, the three primary regression methods really depend on what kind of outcome you have. If y is continuous and you can meet some key assumptions, linear regression is appropriate. Logistic regression is more appropriate for categorical variables. Cox regression is more appropriate for time to event. Linear regression encompasses simple multiple linear regression, analysis of variance, and analysis of covariance. And logistic regression can get just as complicated as linear regression in terms of the amount of covariates that you add to the model. There are other regression methods that I don't have listed here explicitly. If your outcome is a count, you probably want to investigate other methods like Poisson. Negative binomial might be more appropriate if you, again, are like counting the number of times something is happening for a person or a subject or an animal. And Cox regression, again, is not the only method for regression. It's just the most commonly applied method for survival. Any questions about regression methods? Let's go ahead then and finish up with the size of a clinical trial. I have an example here that demonstrates a very simple example of how we determine how many patients we need in order to perform a study. So the process underlying sizing a clinical trial has to do with, again, experimental design. So if you remember back when we talked about what is involved in experimental design, you actually have to have everything in place: the research question, the hypotheses, what outcomes you're measuring, when are you measuring them, how are you measuring them, and how the statistical analysis plan. How am I going to analyze the data before I can even determine how to calculate an estimate of sample size? The statistical method is the mathematics behind it are what determine how big of a study you need in order to meet your scientific objectives with high likelihood. So the things that we have to consider, in addition to how many patients are needed mathematically or statistically, we also have to think about the feasibility of getting that many patients. So I've seen protocols come through that I've had to review for various reasons, where the sample size justification had to do with how many patients are seen in clinic in a year and no other justification. That's not fully appropriate, right? Because we also need to know, if you say you can get 100 in a year, do you need 100? Maybe you only need 20, or maybe you need 1,000 to do the question, to address the question. So you have to also figure out whether or not the study that you're doing will produce some valuable insight into the research question. So we have to consider the mathematics, we have to consider also the availability of patients and resources, the timeline, and then of course the ethical need to prevent any patient from receiving inferior treatment. We want to basically aim for the minimum number of patients needed to achieve the principal scientific objective. And the objective could vary from study to study. You might just be interested, again, in some of that earlier pilot work where you're estimating things, looking for associations. In that case, you're not really doing a power calculation. You're kind of doing your estimate of your sample size is more dependent upon how precise you can estimate certain things that are interesting in the population. Hypothesis testing does result in power calculation because power has a specific meaning within statistics, and it has to do with our ability to find a difference or an association using a statistical test. So just a reminder, we have a couple of error rates, which are our risk. They measure the risk of making different incorrect decisions. The type 1 error rate, which we denote by alpha, is the risk of a false positive finding. In other words, there's a difference between the treatments. There's not a difference between the treatments, but we say that there is. That's a false positive. The type 2 error rate, which we denote by beta, is a false negative finding. And it results when you conclude that nothing is there, there's no significant difference, no significant association, when in fact there really is some kind of impact of treatment on how patients are responding. When we design a study and when we calculate the number of subjects we need, what we're doing is we're trying to get a sample size that will control these two risks at some reasonable level. Generally speaking, again, there's no one universally applied cutoff for both of these. I think we've discussed in a couple of the previous sessions about how we have to really think about the consequences of a false positive finding to figure out if we need it to be really tightly controlled or a little bit less controlled, more relaxed. And also the risk of a type 2 error or a false negative finding. Do we really need to tightly control that, or can we let it be a little bit more relaxed? The type 2 error rate is directly related to the power. Notice I represent the type 2 error rate with a beta. The power is 1 minus beta. Beta is a probability. It's the probability of a false positive finding. So 1 minus beta is the probability of a true positive finding, which is what we want our study to do, right? If there's really a treatment effect, let's find it with high likelihood. And so high power corresponds to low type 2 error rate. And again, it's the probability of correctly detecting a difference between treatments or some kind of an association with a statistical test if that test actually exists. So you often see these risks of making incorrect decisions along with power in a 2x2 table where you have some unknown truth, the null and the alternative, and actually what you conclude from your data. You can see our error rates are in locations where the truth differs from the decision. If the truth is there's no association, but I conclude there is an association, I'm making a false positive. If the truth is that there is an association, but I conclude that there is not, that's a false negative. And this is kind of where we want to exist. We design our study in a way that if our scientific hypothesis is true, we are very likely to find it. But if our scientific hypothesis is not, we are not likely, less likely to flag it as real if it's not actually there. So we usually control alpha and 1 minus beta in our power calculation. The nice thing about sizing a clinical trial in simple cases is that if we know alpha, we want alpha to be 5%, no more than 5%. If we want our power to be at least 80%, so our risk of a false positive finding less than 5%, our ability to find a real meaningful effect at least 80% of the time, then the only missing piece of the puzzle is what are we actually looking for? What is a meaningful difference? And that sometimes is the hardest part of the equation because we don't often know what is meaningful, especially really early on. So it becomes a very important discussion between whoever is doing the power calculation and whoever the scientist investigator is to come up with what the meaningful difference is, what we call sometimes an effect size. There are ways to approach that. I'll show you in a moment with a kind of a standardized measure of effect size. But in general, as a statistician, if there's not a well-defined difference that's being looked for, I usually run and estimate what the sample size needs to be for a variety of different scenarios. And then we try to find a scenario that combines both a feasible sample size and some kind of difference that scientific peers would consider meaningful. So if we have that acceptable, that meaningful difference, then that, along with the type 1 and type 2 error rate, along with the statistical analysis method we're using, will allow me to estimate the number of subjects required to achieve all of the goals of the study. So let's take a look at an example where I'm actually doing a hypothesis test. And the primary objective here is they're actually going to do what could be analysis of variance, but they're going to do a t-test. It's just comparing a continuous outcome between two groups. They want to see, for instance, HbA1c. Is it different when patients are treated with placebo versus when they're actually treated with this therapy A? Subjects are randomized equally to the groups, treatment A versus placebo, and the data analysis plan is going to be comparing the average response, the average HbA1c, of subjects who received treatment A to those who are subjects who were randomized to receive treatment A to those randomized to receive placebo, and we're just going to use a two-sided t-test. In discussions, we decided that the appropriate risk of a type 1 error was 5%, but no greater. So what that tells me is what's the threshold of evidence required for flagging this as a real statistically significant difference. Again, the hard part here is defining what we're looking for in terms of differences in responses between placebo and treatment. When we have a placebo or a standard of care, we often know what to expect for patients who are treated with that. So for instance, this placebo should, based on previous research and previous studies, result in a mean response of about 10. I'm out of HbA1c right now, by the way. But let's just say it's a mean response of 10. I know that based on prior studies, the literature, my own experience. The key here is, what do I wish to detect? So what above 10 or below 10, how far away from 10 do responses need to be in treatment A before I go, that's clinically interesting? That might be a real thing, as opposed to just random fluctuations in this measure that I'm taking. And so it's determined either, again, by pilot data, other studies that have been published in the literature, or your own knowledge of whatever this outcome is that you're measuring, that if treatment A changes response by 10% in these patients, that's clinically interesting. It turns out 10% is actually just a 1 unit difference. You could do it in terms of an absolute difference or a percent. Here I've just got it for whatever reason as a 10% difference. So a 10% difference would mean that they would either see a reduction of 1, that's 10% of 10, or an increase of 1, again at 10% of 10, assuming that the mean response under placebo is 10. And again, we have a discussion about how powerful does this test need to be? What do I want the chances of finding this difference to be? 80%, is that adequate? Does it need to be 90%? 95%? So again, determining what the minimum value of power needs to be will help, again, then set the sample size. So we know the study design is randomized, controlled trial. We're going to use a t-test to determine whether or not the average response is the same or different in two groups. We have our risk of a type 1 error of 5%. We have our power of 80%. And the difference that we're looking for, delta, is 1. If I have all of those things and I know I'm using a t-test, I can very easily calculate the sample size that I need. If I don't know the difference of 1, I might use something else that's kind of a standardized effect size measure. You want to resort to this only if there's no other way of getting a clinically meaningful difference, meaning understanding or knowing what that is. Cohen's d, again, just takes differences between responses, average responses in the two groups, and scales it by some measure of variability in the outcome. So it looks like a T statistic, kind of, right? It's a signal over a noise. And it allows us to figure out how big the difference is between the two average responses as a function of the variation in the data. So if it's much bigger than the variation in the data, then we have a signal that there is a difference. If it's not very big, then it could just be fluctuation in the data, which is what the standard deviation of the data is representing. The nice thing about Cohen's d is that you don't have to specify the numerator or the denominator. If we were doing a power calculation, we would have to specify both the meaningful difference and what we expect the error variation to be, which can, again, unless we've done a lot of pilot studies or there's a lot published in this area, both might be impossible to get. So we only use D when this information is not accessible to us or is not available or it hasn't been generated yet. So we can use D directly It's called Cohen's d. It's really only appropriate in this case when we're doing a t-test comparing averages between two groups. There are other effect size measures that you can use for an f-test and so forth and so on. But d, the nice thing about it is it gives us, without specifying the actual difference that we're looking for, we have kind of a standardized scale. So I can set d to be 0.2, which basically says that the observed difference between the two groups is equivalent to 0.2 standard deviations of the data. They're 0.2 standard deviations apart, or 0.5 or 0.8. And that's called a small, medium, and large effect. You can see rules of thumb are very useful, but also don't really give us, they give us somewhere to start, right? So this is only somewhere to start. And so we can use Cohen's d instead of specifying that there's a 10% difference or and estimating sigma. So suppose we want a Cohen's d of about 0.5 standard deviation. So we want to look for a medium effect because we don't really know what we're looking for. Then we can plug that into a tool. For instance, in RStudio, there's a function called power.t.test where you just specify 3 of these and it will produce the 4th. And it turns out a sample size of 71 per group is required for this scenario. So I have to have 71 subjects in placebo, 71 subjects in control in order to have 5% type 1 error, 80% power of detecting a difference of 1 unit. The key here in any power calculation or sample size calculation is to understand that this is an estimate of sample size, right? That estimate is dependent upon all the things that you put in to estimate it. So if you're wrong about the effect size, if you're wrong, if you're going using pilot data, if you're wrong about the difference that you want to detect, if you're wrong about the error variation in the outcome, all of those incorrect specifications can result in either an underpowered or an overpowered study. So it's always important, I think, whenever you're powering a study, to look at different scenarios and be conservative. So if you get a small change in one of those assumptions that results in a very large change in the required sample size, you might want to think about very carefully what you're doing. And again, the appropriate decision really depends on the context, so I don't want to give an exact example. But the key is, if you've done an adequate power calculation, this is when p-values are meaningful. We've talked about what a p-value is and what it isn't, when it should be used and when it shouldn't be used. When you actually adequately power your study, if you do your data analysis and you observe a difference of at least 10%, and all of our other assumptions about the data prior to doing the experiment kind of play out, then that difference of 10% is really likely to produce a significant result. In other words, you're probably going to flag it with p less than 0.05 because you designed your study to do so. Now, will it always flag it? The answer is no, because you only have 80% power. That means 80% of the time I will flag it. 20% of the time I won't. So it's possible I could still get a negative finding even when I've done everything the right way, and that's the curse of sampling variability. Whenever we power a study for a particular effect, we might observe something smaller than that effect. So if we wanted to find something of 1, a difference of 1, if we observe a difference but it's smaller than that difference that we powered the study for, we probably won't get a statistically significant difference. But we could, because of sampling variability. I'm not even going to talk about that slide. For those of you who are interested in the math, that's what alpha and beta and all that stuff looks like when you assume the null and the alternative relating back to sampling distributions. So it's just a nice slide for you to look at. When we're looking at powering a study, there are some impacts there are some things that impact the required sample size. For instance, choosing the endpoint is really important, because if the endpoint is very precise and doesn't have a lot of variability in it, the outcome is not really it's not noisy, you actually don't need as much data to find it. So a decrease in the error variance results in an increase in power, which is often why we like to use regression modeling strategies to account for the unexplained variation to get a more powerful test. If we increase the difference we're looking for, that actually results in a decrease in the required sample size to achieve power. And that makes sense, I think, because if you're looking for something really big, if it exists, it shouldn't take you too long to find it because it's big. But if you're looking for something very small, it might take more resources to find it. Because it is small, it could get buried in the noise. Increasing your risk of a type 1 error, increasing your risk of a false positive finding, allowing alpha to be a little bit bigger, it actually results in an increase in the required sample size to achieve a given power. And then I think that that's actually reversed. What I mean is tightening or controlling alpha at a smaller level results in an increase in power. There are a lot of interactive web-based tools that show the relationship between power and sample size, power and variability in an outcome, power and the difference that you're looking to detect. I've just linked to one here. There are a lot of tools online that allow you to calculate sample size for simple studies, for instance, the t-test. Often it's easier to use the tool than it is to get the information required to put into the tool. So that's the difficult part, is understanding what do I need and where do I find it. So generally speaking, I mentioned earlier on that there are often different purposes of trials, and this relates back to the lecture that was focused more on experimental design. What's the purpose of your study? If nothing's ever been done, if you don't have an estimate of the clinically meaningful difference, if you don't know what it is that you're looking for, why are you doing hypothesis testing? You should probably be doing a more descriptive type of study, which would usually apply descriptive methods. Let me estimate the average response. Let me get an estimate of the sampling variability, of the variability of the outcome. Those pilot studies, more descriptive studies, are what are required to inform studies where hypothesis testing is employed. So generally, if you're having to rely on Cohen's d, you probably need to be doing a pilot study without inferential tests in order to then adequately, to gather enough information to adequately power a larger future study. And again, that's just employing the scientific method. Any questions specific to today or from any past material? Okay, great. Well, I thank you all for sticking it out for all 4 weeks. We are, of course, always interested in your feedback on the class. For instance, are there topics that were not covered that you'd like to see covered? Are there topics that we spent too much time on that you'd like to see less? We actually use this feedback to change the class every year, which is actually, it informed a lot of changes that I made this year about the content of the class. So any feedback that you give will be anonymous, and we'll use it directly to hopefully benefit the next year's cohort of students. You'll be getting those via email from the same account that's been sending you the information about the recordings, and I'll make sure to send out copies of the cleaned up slides by the end of the weekend. All right, thank you all. Let me see what this... So the question is, can we have online access to these classes? The answer is yes. If you signed up late, you might not have received the email that shows you where the recordings are located, but it is... They are currently located on the Department of Biostatistics website, and they'll be migrated to YouTube. I'd like to clean up the audio on the first, and then I have to pull together 2 different recordings from last week because of the change in classroom.